We won't go into a lot of detail with UV-Vis or ultraviolet-visible absorbance spectroscopy. What we do need to know about it, though, is that it corresponds to the absorbance of ultraviolet and visible light, which combined are typically from about 200 to 800 nanometers, with 200 to 400 roughly being UV and 400 to 800 roughly being visible. Sometimes these are extended out past 800 into the near IR. There are really two components to these spectra. One, their absorbance maxima is basically, if you look at the shape of a curve like these three examples here, the lambda max would be the highest or the wavelength, or lambda, usually in nanometers, of the tallest of the absorbance peaks. And you can see this green one has roughly 3 of them, but we could say that the lambda max, or the maximum absorbance, occurs at maybe 260 nanometers. These also have what's called a molar absorptivity, also known as an extinction coefficient, which is just a function of how intensely they absorb light, and it's typically on a per mole basis and takes into account the cell path length that was used in measuring the absorbance spectra, which are typically collected in solution. So that's basically the intensity, or how much light is absorbed on a per mole basis. Now, the one trend that we want to be aware of is that both of these things, the lambda max and the intensity of the absorbance, tend to increase with increasing conjugation. So here we're looking at an example of 3 different compounds containing multiple carbon-carbon pi bonds. One of them, the N=3 example, has 3 conjugated alkenes and some R groups at either end. And again, we noted the lambda max for that is about 260 nanometers. The lambda max for the N=5 version, which would have 2 more alkenes in this conjugated system, so a conjugated pentaene, would have a lambda max, has several, but the highest one is maybe 340 nanometers. Now, since both of those lambda max are still in the UV or ultraviolet range, we're not going to see these compounds as being colored. Both of these compounds would in fact be white because they're reflecting all wavelengths of visible light. They're not actually absorbing any visible light. To absorb in the visible range, a polyene would need to contain a fairly large number of pi bonds, as is in the case of the vitamin beta-carotene, the absorbance spectra of which is shown here. Now notice the difference in wave numbers on the x-axis. Again, this could continue on out in the visible range to about 800, although for beta-carotene, the lambda max of the absorbance or absorbances are just inside the visible range, maybe somewhere around 450 nanometers, which is why beta-carotene is sort of orange in color. And just to summarize, we have 2 features of a UV-Vis. On the x-axis we have wavelength, and so the peaks, the tops of the signals, are going to be referred to as lambda max and typically have a value in nanometers. And the y-axis is absorbance, and that's sometimes listed, or usually listed, in arbitrary units, but if we think of it as a per mole basis, it'll have an extinction coefficient, or a molar absorptivity, epsilon, which takes into account the concentration of the sample. And the thing for us to know is that the more conjugated an organic system is, the higher the lambda max value, the closer to the visible or deeper into the visible range it is, as well as typically higher molar absorptivities.